Today, we're taking a journey from the realm of dense, abstract mathematical proofs straight into the heart of tangible, real-world data problem solving. We're going to look at the foundational rules of how we actually model data, specifically focusing on a cornerstone of mathematical statistics, the Gauss-Markov theorem. But honestly, what's way more interesting is what happens when the textbook illusion of perfect data totally shatters and how generalized matrix algebra has to step in to save the day.
Here's our roadmap for the explainer. We'll be hitting 1. The multiple regression matrix. 2. The geometry of least squares. 3. The Gauss-Markov theorem. 4. When real-world assumptions fail. 5. Generalized least squares. And finally, 6. The WHLD dementia study.
Before we get into the weeds, I really want you to keep this question in the back of your mind. What happens when our statistical rules just break? Because, well, in practice, data is rarely pristine. It's clustered, it's constrained, and it almost never behaves the way early statisticians hoped it would. So how do we actually find the truth in all that mess? It turns out it requires some pretty fascinating workarounds.
Section 1. The multiple regression matrix, translating to math.
To really wrap our heads around complex data, we first need to pack our variables into an elegant mathematical language. Now, if we try to explain a dependent variable with just one explanatory variable, say using just a person's years of education to predict their salary, we'd use simple regression. But as a classic study of 474 U.S. bank employees showed, doing that can be incredibly misleading. Why? Well, because explanatory variables are practically always mutually related. A person's gender might affect their starting salary, which obviously relates to their current salary, and so on. If you ignore those connections, your estimates are completely distorted. That is exactly why we pack the whole shebang into the matrix equation, y equals xb plus e. It elegantly compresses all those multiple variables into single letters. Y is our vector of observations, x is our matrix of explanatory variables, b represents the unknown parameters, and e is our vector of unobserved disturbances or, errors. It's just an incredibly clean, powerful way to handle real-world complexity. Moving on to Section 2, the geometry of least squares, visualizing the math. Now, what's really fascinating here is how we can completely shift our perspective from pure algebra to physical space. This is actually lemma 1 of our underlying proof. Ordinary least squares, or OLS, isn't just some blind mechanical calculation. Geometrically speaking, it represents casting a shadow. Imagine your data vector y just floating out there in three-dimensional space. OLS finds the closest possible point on the flat plane created by your x variables, which we call the column space of x. It drops a perpendicular line straight down to that plane. That shadow, the orthogonal projection, is your fitted value. And the distance of that drop, that's your residual error, E. It's just a beautifully simple geometric truth.
Section 3. The Gauss-Markov theorem, defining the gold standard.
In the stats world, researchers are always chasing something known as BLUE. BLUE stands for the best linear unbiased estimator. Under perfect laboratory-style conditions, the Gauss-Markov theorem proves that ordinary least squares actually is blue. It gives us the most precise, unbiased estimate possible. Literally, it's the estimator with the absolute lowest variance.
But here's the catch. To achieve this gold standard, OLS demands absolute perfection. It relies on a very strict set of textbook assumptions. And two of these rules are especially fragile. First, that the matrix X has full rank, meaning there's no exact multicollinearity. And second, that we have spherical errors, which means the errors are perfectly independent and identically distributed, homoscedastic with zero correlation. Those are the rules of the game. But as you might have guessed, reality absolutely does not play by the rules.
Which brings us to Section 4,
when real-world assumptions fail, breaking the rules.
This is where the illusion of perfection totally shatters. Let's contrast these error types for a second. Spherical errors assume every single data point is an independent, isolated island, but reality rarely cooperates like that. What if you're studying patients who are clustered within specific hospitals, or analyzing economic data over time? Your data points are related. They share underlying effects, and this creates non-spherical errors, which completely violates the classical Gauss-Markov assumption. If you just naively use standard OLS here, your results might technically be unbiased, but they will be mathematically inefficient.
And this brilliantly illustrates our second massive failure, rank deficiency. Imagine an experiment with linear constraints or a model where one variable is quite literally just the sum of two others. Well, your matrix X is no longer full rank. In the parameter space, this creates an infinite set of vectors that all map to the exact same fitted projection in the observation space. Because of this exact multicollinearity, which is essentially your variables stepping all over each other's toes, individual parameters simply cannot be identified. Standard OLS breaks down completely. The math literally cannot be computed because the matrix cannot be inverted.
Section 5. Generalized least squares, or GLS. The generalized heroes.
So, our standard math is broken. How do we fix it? We do it with a rigorous three-part mathematical proof. We already talked about Lemma 1. OLS is an orthogonal projection. Lemma 2 steps in with some heavy math involving the positive semi-definite order to prove OLS minimizes variance, basically showing that any competing estimator out there has strictly non-negative excess variance. And finally, Lemma 3 brings in our hero, generalized least squares, to handle those tricky non-spherical errors.
So how does Lemma 3 actually pull this off? Through a brilliant piece of math called the Cholesky decomposition. Think of it like a giant statistical washing machine. It takes your clustered, messy, correlated data, runs it through a cycle, and transforms it back into independent spherical data. And once the data is transformed, boom, the classical OLS rules from Lemma 2 apply perfectly again. It's an incredibly clever trick that reduces a complex, broken problem back down to a solved one.
Section 6. The WHLD Dementia Study, Real-World Stakes. Let's actually take all these abstract concepts and apply them to a high-stakes puzzle. We're going to look at baseline clinical data from the WHLD Dementia Study. We are analyzing 843 service users distributed across 57 residential care facilities. Now, patients in the same facility share facility-level effects, right? Which automatically creates those non-spherical correlated errors we were just talking about. Furthermore, the model includes individual neuropsychiatric inventory, or NPI domains, right alongside an NPI total score. Because the total is literally just a sum of those domains, we have exact multicollinearity. We have deliberately built a model that aggressively violates the two main classical Gauss-Markov assumptions.
So, the crucial point is right here in the data comparison. First off, standard OLS would instantly crash on this data because of the multicollinearity, but by using a generalized mathematical workaround called the Moore-Penrose pseudo-inverse, we bypass the crash and successfully map the projection anyway. Next, just look at the difference in the estimates. Because the patients are clustered, standard OLS point estimates, while technically unbiased, are mathematically inefficient. When we apply generalized least squares, assuming a plausible intraclass correlation, the estimates physically shift. Hallucinations move from -0.15 down to -0.30. Agitation moves from 1.21 up to 1.36. In critical medical research, relying on the wrong math leads to inefficient estimates. You absolutely need robust estimators when dealing with real-world structures. There's just no way around it.
Ultimately, what this generalized framework teaches us is pretty profound. When your matrix is ranked efficient, you just can't pin down individual parameters. The actual unit of mathematical inference isn't the single variable, that non-unique beta. Instead, it's the estimable linear combinations. It's all about the relationships and the geometric contrast between variables, rather than the isolated variables themselves. The Moore-Penrose pseudo-inverse rescues our projections, allowing us to find the absolute best linear unbiased estimates even when the data stubbornly refuses to cooperate.
Which leaves us with this final thought. We rely on data to make huge decisions in business, in medicine, and in public policy every single day. But are the hidden mathematical rules in the data you interact with secretly being violated? Are you assuming your data is a pristine sphere when it's actually a clustered, correlated mess? The next time you look at a regression output, remember the geometry behind the numbers, and don't be afraid to ask if you need a generalized hero to find the real truth. Thanks so much for joining me on this explainer. Keep questioning the data.